Yesterday what I told means I am not here to parent you. Right? Those who are feeling that you need parenting, go home. Get it finished, come here. Back. Okay. So here we will start. Viewpoint we have already done, right? Uh, that is another problem which you can. That is regarding the dew point. Another problem we have discussed what is dew point in the last class, right? What is that? What is that? So dew point means basically when you have some moisture in the mixture, when you cool it at the temperature, where cooling means you are basically reducing the temperature. When you reduce temperature at a particular temperature, the moisture will make the mixture saturated, or the mixture will become saturated with the moisture, present moisture. You are not adding something, right? In case of dew point, you are not adding moisture, simply you are reducing the temperature, and with the existing moisture the mixture will become saturated. And if you reduce the temperature further, the mixture will basically that means the moisture will be separated as water and it will form dew, right? Condensed water, right? So that is called dew point. Where so dew point means you are reducing temperature, and when you are adding moisture and moisture to make the mixture saturated at a particular constant temperature by adding moisture, there is the concept of relative humidity comes. Means basically definition, right? But definitely at any point of temperature and pressure you can calculate relative humidity. What is the definition of relative humidity? We have discussed in the last class. Again we will discuss in detail during the discussion of module 4, that is air conditioning. Okay. So if we want to calculate, for example, what is the problem? I will shortly discuss this. Determine the molar analysis of the product of combustion when octane is burned with 200% theoretical air. By this time you know the meaning of this air, and determine the dew point of the product if the pressure is 0.1 megapascal, that is 100 kilopascal. Total pressure is 100 kilopascal. So what is that? Determine the molar analysis. That means you have to calculate the moles, right? And you have to calculate the dew point. That is the problem. Okay. So what is given? Octane is the fuel. It is burning with 200% theoretical air. So you know if octane is burning with stoichiometric air, what is the reaction? Then 200% simply multiply 2 with that. Right? 200% means you will multiply 2 with that, and 1 excess. So one of these two is absorbed in this, and another one is excess air, that is oxygen. And definitely the nitrogen will be twice of simply equal to that. Is it clear how to get the reaction? Very simple. Just balance the atoms, carbon, hydrogen, oxygen, and nitrogen. You will get it. Okay. Next, molar analysis. So product of combustion. What are the products? What are the components of the products? CO2, H2O, O2, and N2. Because excess air is there. 200% theoretical air means excess air, oxygen will be there. So oxygen and nitrogen. Is it clear? Then what are the number of moles? You can directly write. So 8, 9, then this is 7.52. Sorry, nitrogen it will be multiplied with this. So it will be 94, is coming to be 94, and oxygen is coming to be 12.5. So total number of moles you can calculate just by adding this. Clear? Therefore, you can calculate what is the mole fraction. So mole fraction how to calculate? Divide this by this, you will get this. That is percentage, in percentage definitely. It will come to be 0.0647. So in percentage it will be 6.47. So if you divide this by this, it will come to be 0.0647. But according to percentage, when you multiply with 100, it will be 6.47. Accordingly, all these are there. Okay, is it clear? Mole fraction you can calculate. Clear? Clear or not?
Yes, sir.
Okay. So partial pressure how to calculate? What is the definition? What is the definition of partial pressure? In the last class I discussed that. Actually I forgot to bring them in. So what is the definition of partial pressure? Can you become? Okay. What is partial pressure? Can you recall? Say partial pressure. Partial pressure P. Partial pressure of any, say for example CO2. What is that? Total pressure multiplied by mole fraction. So partial pressure of CO2 is equal to total pressure multiplied by mole fraction. What is mole fraction? What is that? Exactly. N CO2 divided by N total. Okay, once the pen comes, I will add. So try to understand that. You write partial pressure of CO2, that is PCO2. PCO2. Partial pressure of CO2, that is PCO2, is equal to P total multiplied by YCO2. Sir, get it started here. Hello. Okay. So that is partial pressure. Once we have discussed it earlier, what is partial pressure? Hey, listen. So this is your mole fraction, and partial pressure will be basically total pressure multiplied by mole fraction. That is partial pressure. Okay. So simply it is weighted to the mole, number of moles. Okay. Next is, therefore, once this mole fraction is known, partial pressure of water, total pressure of water is 100, total pressure of the mixture is 100, that is 1 megapascal, 0.1 megapascal mentioned. So 100 kilopascal, 1.1 megapascal means 100 kilopascal multiplied by this. What is that? Mole fraction of water. 7.29 means 0.0729. That is mole fraction in terms of fraction. So it will be this much. Okay. So that is the pressure of the vapor in the mixture. Partial pressure of vapor. Now how to get the liquid? We have discussed in the last class that you see that this is the dew point. So this, if this is known, then I can calculate what is the saturation temperature at this pressure from the steam table. So you can determine what is this temperature at this pressure from the steam table simply. So that is the dew point technology. So I ask you to bring steam table tomorrow. Okay. Yeah. So that way you can calculate what is the temperature, and this is the problem. Solved, right? Next is exhaust gas analysis. So far what we have done is combustion analysis, that is forward combustion analysis. That means knowing the fuel, we burn it with some amount of air and then we get the products. So whatever happens, we analyze. So this is the forward way, right? Next is predicting the composition, that is of the product is relatively easy. When we know the fuel, that means the forward analysis is relatively easy. That's why knowing it, prediction is easy. Prediction means what can happen. That is easy. For complete combustion. Complete combustion means what? When we know that complete carbon will be converted to CO2 and complete hydrogen will be converted to H2. There is no other thing that is happening. But if it is not happening like that, for example, some of the carbon is converted to carbon monoxide, some is unburned carbon, right? Some is something else, right? Say for example, hydrogen, you have hydroxyl radical, clear? So that time it is not easy to predict, right? So you do not know how many components are there. How can you write the chemical balance equation, right? So you will not be able to. If you do not know the complete reaction, then you will not be able to balance it, because how much is CO2 and how much is CO, if you do not know, you cannot write. Clear? So therefore, what is done is, another way is, you get the product of combustion. You have the product of combustion, that means you burn it. Exactly, and most of the time, complete combustion does not happen. Right? Even if you supply excess air, even if with excess air, right? See, even if with excess air, you see that there is simply one of the point is there. You see that even if with excess air, there is less chance that it will be complete combustion. Okay, so even in the presence of excess air, so that means complete combustion is not possible. That means what is the meaning? That when you have fuel and air, for complete combustion, what is needed? There are three reasons for incomplete combustion. One is insufficient air, second is insufficient mixing, and third is dissociation. Right? If these things, at least one of these things happen, then combustion will be incomplete. Right? So that means ensuring complete combustion is hardly possible. So you cannot write the reaction, right? And therefore you cannot balance it, right? So what is done rather is, we directly burn the gas, directly burn the fuel and get the products, then analyze the products itself. So we analyze the product itself. So what is done therefore? You get the individual components, that means chemical analysis you do. Then you get the exact components, what is the fraction, that is volume fraction, and then try to predict what happens. Right? So that is the thing that is called exhaust gas analysis. Okay. So commonly used device that is there is called Orsat gas analyzer. Okay. So, and the results are reported on dry mist. That means first the moisture is absorbed and then the remaining exhaust gas is analyzed. So it is dry mist. So how it is done? You see that this is also gas analyzer. you may see that in your laboratory in your 6th semester. So this is Orsat gas analyzer. Here mainly 3 gases can be analyzed in the products. One is oxygen, that is if there is excess oxygen, then carbon monoxide and carbon dioxide. Okay, 3. And the remaining thing that is there that will not be analyzed, we will assume that this is nitrogen. Because in the products you can have what? Water. So you are absorbing the water. Then you can have CO2. So CO2 is there. If there is excess oxygen, you can analyze that oxygen, that is presence of oxygen by chemical analysis. You can analyze, and then carbon monoxide if it is incomplete combustion, right? And the remaining, whatever will remain by absorb. Actually, what we will do, we will take some exhaust gas sample, and then we will collect it, and then that is, for example, 100 ml we will collect. Okay. Then out of this 100 ml, we will selectively take chemicals. What are the chemicals here? The most common absorbents are that is they will absorb the gases, and therefore the volume will reduce, and therefore we will predict that gas was present in the mixture, and that is absorbed by a particular chemical, and therefore the volume will be reduced. Right? So what is the volume reduced? That is corresponding to oxygen, that is corresponding to CO2, that is corresponding to CO. That, and finally, what will not be absorbed, we will assume that this is nitrogen. That is called the exhaust gas analysis by Orsat. So here you see potassium hydroxide or caustic potash for carbon dioxide. It will absorb carbon dioxide. So it will pass the mixture through that sample, that is caustic potash solution. Then after that, it will pass that through pyrogallium. Pyrogallium is pyrogallic acid for oxygen. It will absorb oxygen, and then finally it will, that is copper 1 chloride, that is called cuprous chloride, ammoniacal cuprous chloride. So it will basically supply that. So there will be basically one hydrochloric acid. In hydrochloric acid, copper sticks or copper rods will be immersed, and there it will create cuprous chloride. Okay, so you will not exactly use cuprous chloride. During reaction you will use it. Okay, so copper sticks will be immersed in hydrochloric acid. So for this carbon monoxide. So once you do these 3 in sequence, whatever will be absorbed, you will calculate that by noting the values, volume reduction, and finally whatever will remain, that is nitrogen. So you will list it, and then molar analysis you can clear. So exhaust gas analysis you can do, that is also called reverse combustion analysis. I am just giving one example. Say for example, methane is burned with atmospheric air. Methane is burned with atmospheric air. The analysis of the product on a dry basis is as follows. Okay. What is the meaning of dry basis? That in the products definitely there will be H2O, but the analysis is based excluding H2O. Okay, so you see that there is no H2O in the list, right? So you see what is the percentage total? 87, then 10, 97, then 2. It will make it 100, right? So H2O is excluded. Therefore, this 100 is actually comprising of volume, right? That is called dry basis analysis. Next, what we do? Calculate the air-fuel ratio and the percent theoretical air and determine the combustion equation. Clear? So, what is expected? You see, now it has reversed. That means initially what was told, that the fuel is this, then you warm and determine the reaction. Whatever happens in the gas, whatever happens in the products, you determine. That was called the combustion analysis forward. Now it is reversed. Only the product of combustion is given, analyzed by analyzing, say for example, by some gas analyzer. Right? You see, in your
car, right? Pollution check, right? But you do basically what is the exhaust gas composition, right? They do it, right? So like that. So here we do so that we check that it is under pollution level or not, the safe level or not, right? So here also some kind of analysis is done and we check that these are the values: CO2, oxygen, CO, and nitrogen. Where so kind of say for example by Orsat. So you see CO2, oxygen, and CO can be analyzed by Orsat. So for example, you take that this is by Orsat analyzer. So in our lab we have one Orsat analyzer. Also we have some catalytic component, right? So these are the mole fractions given. Mole fractions given. So what we have to do? Calculate the air fuel ratio at the percent theoretical air and determine the combustion direction. What is given? Atmospheric air. So what is the meaning of that atmospheric air? What is the meaning of that atmospheric air? Actually, I have to switch between these because I cannot write today. Forgive me. So what is the meaning of that? What is the composition? O2 plus 3.76 N2. So whenever it is mentioned that it is atmospheric oxygen, O2 plus 3.76 N2. Then you can write. Clear? Next is that is you have to understand the problem statement. That is the first thing. Investigation. Whenever you have been, that is like a detective. Whenever a problem statement is given, you have to investigate that where I will get a clue. That is like an investigator, detective, right? So here, what is the clue? Clue is that it is atmospheric air. Therefore, immediately you know what is there within the bracket. O2 plus 3.76 N2. Clear? And you know methane, right? So when you try to write the structure of the reaction, you know methane on the left hand side, then O2 plus 3.76 N2, but outside bracket what is the mole number you do not know. You have to determine that. So, but you can write the structure at least, right? Whatever is in the left hand side, and what is in the right hand side, that you also know, because this is the composition excluding what? H2. Along with that, H2 will be there definitely. So for balancing the reaction, H2 you have to write, but excluding H2 is excluded for this composition. Is it clear? So therefore, if you write this, if you say for azimuth, say 100 kilomole of dry product is there, then you can directly write what is the individual number of moles for CO2, CO, O2 and N2. Is it clear? That is, if you assume that you had taken 100 kilomole of dry product, then immediately you can write what is CO, CO2, N2 and O2. And H2O will come as a result of balance. Is it clear? So investigation is going on. Is it clear? So how to determine the unknowns? Right? That is the solution. Clear? Let us write the conversion equation for 100 kilomole of dry products. Clear? So as you know, so accordingly you move. Right? Clear or not? That is wise thing. Clear or not? Is it clear? Okay. Next is because that will be your problems in that exam. Okay. So from the analysis of the products, the following equation can be written, keeping in mind that the analysis is on a dry basis, excluding H2O in the product of combustion. Okay. So therefore, what I can write is on the left hand side. Oh, okay, that will come as a result. I have written for just its extra intelligence. You can assume. But the thing is that they can be combined. Atmospheric air. So you know that this is that C is equal to what? B multiplied by 3.76. That's it. Okay. Just I have written a different. I will give you a different test. Okay. And this is 10. This is 0.53. This is 2.3. D is unknown because H2 was not included here. So H2 is excluded, and this nitrogen. Okay, is it clear so far? So can we do the balance? We have nothing to do, just atom balance. We can do. Okay, so you can do this. Simply you write this, you know by this time what to do, right? So write the equations, just balancing. So what is this, what is that, you know. That means this carbon is present in this and this, but carbon is present here only. So what is the total? 10.0 plus 0.53 is equal to A. So that way you can write the equation. Is it clear? I am telling you, you know it, right? By this time you know. Clear or not? So you have to just write A, B, C, D, carbon, hydrogen, nitrogen, oxygen, balance. So by doing these you can determine A, B, C, D. Is it clear? Is it clear, everyone? You have to practice at home. Whatever I have supplied, so you have to read and practice all the problems. Okay. Now check. You can check it. Finally, there can be a check. That is, since you have say 1, 2, 3, that is, there will be a check because you have one extra equation. One extra equation. So what you can do is basically, because you see that there will be a check. So once you determine B and C, you can always check whether C by P is equal to 3.76 or not. Is it clear? Because this is atmospheric air, so I have just given it an unknown. Actually, there is one unknown, but I have written two unknowns. So you can check whether this by this, that is C by P is equal to 3.76. So you can see that. You can see the C by 3.76 is equal to this, and this is this. Okay, so 2.23, that is B. B is equal to this. So C by 3.76 is coming to be B. That we have checked just. Here, or you could write simply within bracket B multiplied by O2 plus 3.76 into. That also you could do simply. Okay, you can make things simple. Is it clear? Next one. So finally you rewrite it after just replacing the values here. That is the final reaction. Dividing flow by 10. What we are doing basically? We are writing the chemical reaction for 1 kilomole of the fuel. So on the left hand side you have 10.53. So if you divide the whole reaction equation, chemical reaction by 8.53, then you will get the chemical reaction for 1 kilomole of the fuel. Generally that we do, right? So we can write it. That is the final reaction. Okay. Clear? So exhaust gas analysis. One example. What? 10.53 is the number of moles that was determined. A is equal to 10.53. So we have written the equation. This reaction for 100 kilomole. This reaction is for 100 kilomole of products without H2. That reaction. But when I divide the whole reaction by this, I will get here 1. That means this reaction, same reaction, but with 1 kilomole of fuel. Is it clear? So that completes the exhaust gas analysis. So we have done what? Combustion analysis, forward as well as reverse combustion analysis. What is the means when you know complete combustion, you can go for forward combustion analysis. If it is complete combustion, you can go for forward combustion analysis. If you do not know whether it is complete or not, then you analyze the product itself and from that try to predict the reaction. Okay, that is the philosophy. Okay, is it clear? Okay, you can do some. Okay, air fuel ratio was needed, so you know how to calculate air fuel ratio simply, right? Mass of air by mass of fuel. and also you can determine the equivalence ratio. So what is done? You see the air fuel ratio on a mole basis. Air fuel ratio on a mole basis is, what is that? Here you see that 2.2 is written oxygen. Total mole air fuel ratio we will calculate. This is, what is that, on a mole basis. It is asked on a mole basis. So total number of air molecules or air moles is how much? 2.2 plus 8.27. So that is air. And what is the number of moles here? What is the number of moles here? 1. So what is the air fuel ratio on a mole basis? So air fuel ratio on a mole basis is this divided by this. So total 2.2 plus 8.27 divided by 1. That is equal to 8.47 kilomole of air plus 1 kilomole of fuel. That is air fuel ratio on a mole basis. Right? And air fuel ratio on a mass basis, how to calculate? Simply multiply this with this, that is the molecular mass of air. So this multiplied by this divided by 16. Why? Mass of 1 kilomole is 16. 12 here and 4 here. So it is 16. So it is 18.97 kg per kg of fuel. Okay? Kg of air plus kg of fuel. So both, that is air fuel ratio on a mole basis as well as air fuel ratio on mass basis, you can calculate. Is it clear? Now the theoretical air fuel ratio you can calculate for within theoretical air fuel ratio. So simply write the stoichiometric reaction. So it is this. So theoretical air fuel ratio is this 17 and this is this. Theoretical. So why we are doing that? Because we have to calculate the excess air, percentage excess air. Percentage excess air. Okay. So theoretical air fuel ratio is this. And therefore, what is the excess air? That means you have some excess air, right? So that is per mass basis, right? So, and we know that in our earlier discussion, we know that mass basis or mole basis, theoretical percentage will be same, right? We have written it, right? It's 110% theoretical air. Simply we have multiplied with 1.1. So here also, therefore, if we can calculate what is the percentage, so this will be the percentage excess air. We don't need to go for molar basis analysis again. From mass basis analysis, you can do directly. So actual air fuel ratio divided by theoretical air fuel ratio is the multiply with 100. You will get the percent theoretical air. Is it clear? That is exact amount of air fuel ratio divided by the theoretical, you will get the percentage theoretical air. Okay? Clear? Okay. Next we will enter into the what is the name? Melting. So we will now enter into the energy analysis. So far we were discussing the mass analysis, right? Now we will enter into the energy balance. Okay. Actually, for that I need that pen. Okay. So I will discuss orally. In the next class I will discuss in detail. Or you can ask some question. We can continue with the mass class. The next class we will discuss the. Okay. Briefly I will discuss. Then in the next class I will elaborate. Okay. So you see that in case of energy analysis for combustion, it is completely different from whatever you have learned earlier. Why? Because in earlier thermodynamics, whatever in the reactant side and whatever on the product side, say for example any kind of equilibrium, you have some reactant, you have some products, right? So that means you have a chamber, that is the thermodynamic control volume. Something is entering and something is leaving. So whatever is entering, we can call it
reactants, and whatever is living we can call it products, right? In case of, say for example, a boiler, it's a control volume boiler, or a turbine, whatever you have analyzed so far, steady state, steady flow, or steady flow energy equation, right? Steady flow devices. What was the thing? That means something is entering, which is basically say liquid water in boiler, and something is leaving, which is vapor. But they are always H2O. Chemically there was no change, right? So the advantage was that you could directly read that from the property from the steam table, right? You know pressure, that is state, that is called the thermodynamic state. You know temperature, you know pressure, and you can directly read that from the steam table. You don't need to go somewhere else. Clear? But in chemical reaction, what you have? CH4, that is methane, plus air and producing CO2, H2O, nitrogen, right? In general, nitrogen for complete reaction. If you have incomplete reaction, then you do not know, right? It can be carbon, it can be carbon monoxide, it can be hydrogen, it can be H2O, it can be OH. So many things can be possible, right? So all that means properties for all chemicals will be involved there. If you want to analyze the energy equation, then energy terms for all these will be involved, definitely. So energy balance, then what is the energy balance? Energy before reaction is equal to total energy after reaction. That is the thing, right? That should be the thing. That means energy. That means in boiler, what you do basically? You supply some water, some H2. Say for example, some enthalpy at the entrance, some enthalpy at the exit. So what you do? Enthalpy at the exit minus enthalpy at the inlet is equal to whatever heat supply. That you do. That means total energy before the process is equal to total energy after the process. You write the steady flow energy equation here and you write the terms. Clear? Here also, that simple steady flow energy equation will be valid. Or for example, if it is a control system or closed system, that kind of energy equation is valid, but the terms will be different. In that case, simply enthalpy of hydrogen, say for example air, or simple enthalpy of say H2O was enough. But here you have to go for a shift. That means, what is chemical reaction? Can you tell? What happens during chemical reaction? In simple words. What is chemical reaction? In simple words. Some chemical bonds are broken, some new bonds are created. Clear? And I have told already that when bonds are broken, what happens? I have to break the bond, I have to apply my energy. So energy is absorbed. When bond is broken, energy absorbed. Means if I want to break your friendship, I will pay you something. I will pay you and you will break your friendship. So I have to pay something. You will absorb some money and there will be some in your pocket. Right? So that means before breaking, I am giving an example by which you can understand. Please follow. Okay, otherwise you will not understand. Say, initially you had some money, you have sacrificed some benefits, right? Now I give you some temptation that I will give you something, you break your friendship. So what happens? I supply some money, you take it in your pocket. So how many pockets are there? 6 pocket, 8 pocket, whatever. These are the modes of energy. These are the different modes of energy: kinetic energy, potential energy, different pockets. In this pocket kinetic energy, in this pocket potential energy, in this pocket chemical energy, in this pocket latent energy. Many energies are there. Whatever you want to absorb, I will supply. Okay. So you have some kinetic energy and potential energy. I give you some money. That means this, and you take it and you break. So before that breaking, individual what energy you had, after breaking what is your energy? Is it increased or decreased? Individually increased. That means my energy, what was in form of thermal energy was supplied, right? And you absorb it, and it becomes your potential energy. Because this is potential energy. You are not showing it. Your potential, you are not showing it. Right? Potential means what? You have something, you are not showing. Right? I have the potential. So you are not showing it. You are keeping it. Right? So I am giving you, you are storing it as potential energy. So when you store, it may be in the form of potential energy. If you run, it will be in the form of kinetic energy. So whether you are running with that or you are keeping with it. So that will be either potential energy or kinetic energy. Right? So that means when I supply energy, your energy level increases. That energy here we will call chemical energy. That means when I break a bond and you absorb that energy and you keep it with you, that is actually chemical energy. That means I have supplied thermal energy and you have absorbed it. That is an endothermic reaction. That means breaking of bond is an endothermic reaction, and you are absorbing that energy and you are keeping it with you. That becomes your chemical energy. That means in endothermic reaction, thermal energy is converted to chemical energy. Right? In exothermic reaction, that reverse happens. What happens? You create a bond. Initially, you had some chemical energy. Now you create a bond, you sacrifice that chemical energy, and that is released in the form of thermal energy. Clear? So you say that okay, I want to make a friendship, then please accept so that we can make a bond. So you give me some energy, so that I accept and I allow you to make that. Clear? Okay, thank you. Next day I will discuss.